Okay, we are 5 past the hour, so I'm going to go ahead and get started now. So I want to thank each of you for joining in for the training today titled Getting Your Software Running on ROAR. So my name is Justin Patucci, and I'm a staff member at the Institute for Computational and Data Sciences, known as ICDS. So our institute builds and maintains Penn State's main high-performance computing system, and we offer training sort of around the use of that system and sort of centered around HPC. So today we'll be discussing some different methods, different ways you can sort of use to get your software installed and running on the ROAR systems. So this is a very common request that we receive in our IASK Center, which is our main support department for users of our system. And so the idea with this training is to sort of educate the users so they can sort of take on that task. I don't want to say take on that burden themselves, but as someone who does their own research, it is sort of, one goal that I have is to sort of rely on as few people as possible. So if I can sort of take ownership of my own software stack, then I don't have to worry about sort of depending on anyone else. So this sort of one goal for this training is to sort of empower our users to be able to install and sort of take a handle of their own software. Just in terms of logistics, we have a extremely small crowd today. So if any questions come up, feel free to just unmute yourself and stop me as soon as the question arises. You can also sort of put your question in the chat if you'd like, and I think maybe Jason or I can routinely monitor the chat if any questions come up. But I would sort of prefer just unmute yourself and ask the question sort of right when it happens. That way we can sort of address it while it's hot. The link to the slides are here for your future reference, and I will go ahead and get started. So this is a overview of today's talk. I see something coming in the chat, so I will. So Lindsay's just putting the slides in the chat for your reference. So this is an overview of the session today. We're going to go over a few software installation options that you have as a user of the ROAR systems. Some of those are specific to the ROAR systems. Some of them are sort of general for any Linux-based systems. So some of these skills are definitely transferable sort of outside of Penn State, outside of ROAR. And then we're going to sort of jump into hands-on components for each of those different options. So we'll see an option compiling code from source, using a user-level package manager, and also Singularity. So we'll sort of go through the whole spectrum of different options that you as the user can sort of take advantage of in terms of getting your software installed and running. So goals really quick, sort of obviously align with that content outline. We want to educate you on how you can get your software installed and running. We'll really scratch the surface and learn a little bit about build systems, package managers, and containers. It's really just sort of laying that groundwork, that foundation for you as a user to sort of take the deeper dive. And then along the way, we'll learn some general best practices. I have here experience is the best teachers. So we're going to have some hands-on sections, as I mentioned in the review of the content slide. It really helps me, at least, to solidify concepts and solidify things if I go through sort of on my own time and reproduce, things that I learn in hands-on sessions. So I certainly encourage you to do that. Go back through this and sort of rework those examples if this is all new to you. Okay, so some motivation, why are we talking about installing software? Maybe you come from a Windows world where installing software is sort of downloading a file, double clicking and not reading terms of service and sort of clicking along. So in Linux, in sort of research computing that is primarily conducted in Linux environments, it's a little bit different. And that's not to say that dependency problems and issues can't arise in a Windows sort of OS. But so we have something referred to as dependency hell, and we see a sort of a graphical depiction of dependency hell on this slide. And so dependency hell is sort of summarized where you want to sort of install package A here, which is on the left side, and you can see package A isn't just a single entity. Package A depends on many different things, and then those dependencies themselves have other dependencies, and sort of down the rabbit hole you go. And you can see from this sort of this graph, these dependencies can get out of hand quickly, and you know, having to go through and resolve and make sure each of these dependencies are met can be a real problem and a real challenge. So that's one of the sort of main motivations of why it can be difficult to install software yourself. Software projects can be simply very large, you know, thousands of source files in terms of size, and sort of going through and compiling that by hand could be sort of time consuming. There's all sorts of version conflicts that can come into play. You know, if we look at this graphic into the right, you know, we could have a dependency of a dependency that requires one version of a library, and then maybe another version is required for another dependency. So, you know, again, those are all things that can cause problems and can make this sort of challenging. There's limitations in terms of operating systems. Sometimes when you pull down a precompiled package, it's only compatible with a certain flavor or a certain version of an operating system. It can be difficult, or again, time consuming to have an intimate knowledge of the system you're running on in order to take full advantage of optimizations. So on our system, we have certain flavors of Intel processors, and you have to you know the instruction sets that are compatible with those processors in order to take advantage of those optimized instruction sets. Another challenge with software can simply be licensing. You know, getting a license manager stood up and getting that figured out is something that takes time and effort. So sort of all this goes into to serve and to motivate, you know, why we're talking about installing software, and sort of why it can be difficult and a problem. So we see here sort of a graphical depiction, a graphical hierarchy in terms of your options for getting software installed and running, or using software on the ROR systems. And sort of this is ordered in terms of, at the top, it's sort of the least amount of effort on your part. And as you sort of go down and follow that arrow, there's more effort, more burden on you as the user in terms of getting your software installed and running. So sort of as you walk your way down here, you know, while it can be more challenging to install you know, compile, build software from source, that also gives you the sort of the most number of knobs to sort of tweak and to turn in order to make your compilation, to make your installation as optimal as possible. So as I mentioned, we're going to sort of hit on each of these items individually in detail, and also with a hands-on component. So starting at the top with sort of the easiest from the user's perspective is our central software stack. So we have a list of software, 100+ packages that we make available sort of by default on our system. And we make these available through module files. So module files are nothing more than a nice way for you as a user to use software. So I have here on the slide some different module commands that you can use in order to utilize software. So the module spider command will, if you open up a terminal in our system and you ran the module spider command, that would give you a exhaustive listing of all the software that exists on our central software stack. And if you run module spider and you see the software that you need available on your stack, the software that you need available on that stack, then you're sort of you're done at this stage, right? You can sort of stop right here at step one and be done and start your research. If you don't, we'll go through your other options. So module spider is one command that you need to know. And then once you find a module file that you need, or the software that you need, you can use module load to load that module file, which sort of all it does behind the scenes is sort of set up your environment so you can use the software. So if I would do module load ANSYS, it would set some environment variables sort of behind the scenes. So whenever I ran an ANSYS command, the system would know sort of what that means or what to do with that command. You don't have to use module files on our system. Again, really all it's doing behind the scenes is modifying your environment. It's sort of a nicety for you as the user. We have module families on our system. So in these module families are centered around different compilers. So we have the GNU GCC compilers, we have the Intel compilers, and we also have the PGI compilers. And there's whole sort of suites or families of software sort of built for each individual base compiler. So for example, the GCC family, we have a GCC version 5.3.1 family, and within that family, there's a version of OpenMPI, which was compiled with that compiler. And then there's a whole sort of suite of software that was built using that version of OpenMPI. So just know that if you run module avail, which is another sort of module command that will give you a listing of software that's available, that will only give you a listing of the software that's available in the family that you're in. So just sort of to leave no questions asked, use module spider initially to see what's sort of exhaustively on the software stack. I have some other sort of module commands that you'll need to know. I'm not going to touch on them sort of right now, but just know that module load, module spider, I guess module list that will tell you the modules that you have loaded. They're really sort of self-explanatory. Okay, so now I just want to sort of hop over and have a hands-on example just to sort of show you what's on the software stack. So for that, in the subsequent hands-on sessions today, we're going to take advantage of our Open On Demand web portal, and you can go to that web portal by visiting this URL here. So if you open up a web browser and go to portal.aci.ics.psu.edu, log in. As long as you have an account for the ROR systems through ICDS, you'll be able to access the full functionality of that portal site. So I'm just going to hop over there myself. So if you go to portal.aci.ics.psu.edu, you'll sort of land on this homepage, which is currently loading. You'll have some information about some storage if you have access to storage and different allocations. I'm not going to sort of go through the functionality of this portal site, but if this is the first time that you're seeing it, I encourage you to sort of click on the different aspects of this main menu up here with the file browser and things along those lines. But what I'm going to do is have you guys initiate an interactive desktop session. So for that, if you go to interactive apps in ACI interactive desktop and click that, you'll be presented with this web form. And with this web form, select GNOME 2. For the allocation, select open. For the number of hours, select 2. And for now, let's have you try standard core. But if that fails, and by fails, I mean takes a long time to load, you can come back and select basic core. So once you have one of those selected, hit launch. And behind the scenes, this will sort of submit a job to our scheduling system and look for an open slot amongst our compute nodes to run that job. So you should see this sort of this box with a gray area near the top telling you that the job is queued. Once your job starts, that will turn green and you'll have a little blue button to launch your desktop session. So I'm going to delete my job here so I don't unnecessarily take up resources because I already have a job scheduled. So once you click that button, what will happen is you'll be thrown into a desktop session directly in your browser. So this is a desktop session running on one of our compute nodes, all within the browser, all without having to install anything. So at this phase, hopefully everyone who has an account is at least at the stage where they submitted a job. If not, sort of raise your hand in the chat, or raise your hand through Zoom, unmute yourself, or put something in the chat, and one of us will sort of help address that. But I'm going to sort of show you this module spider command. So if you go to Applications System Tools Terminal, you can open up a terminal, and I'm just going to make this a little bit bigger. So if I do module spider, this will give me a list of all the softwares. You can see Abacus in alphabetical order with a short description, sort of, and you can hit the space bar to tab your way through that that listing. If I see something I want, like module load, so if I want to load something, so module load GCC, which is again a compiler, I can do module list to make sure I have it loaded. If I want to see what that module file is doing, I can do module show. And you can see here, all it's doing is prepending some paths to some environment variable. So the path environment variable, LD library path, so on and so forth. So like I said, you don't have to use module files. They're more of a nicety. If you want to manually set up your environment yourself, go for it. All of our software lives in opt ACI. So you can shop around in there to see what you need. I would encourage you to use module files, but you don't necessarily have to. I think that's it in terms of showing you the software stack. It's pretty simple. Module spider, see if what you need is there, and then module load. So I'm going to hop back to the slides now. Any questions come in? I'll check the chat here to see if anyone was having trouble. Seems to be okay. Again, we'll just let your jobs sort of sit there in the queue until we get to the next hands-on portion. Oh, no questions? Okay. And then if you notice your job isn't starting in 10, 20 minutes, go ahead and leave it in the queue, but submit another job with a different node type, and we'll try to get your job pushed through that way as well. Okay, so compiling from source. So this was sort of at the bottom of the sort of hierarchy process that I described in terms of most amount of effort from the user's end. So to compile it from source, there's some things that you need to know or need to have as a user. You need access to the source code, obviously, and a compiler. So compilers we have on our system, but in terms of the source code, if that's something you're bringing yourself, you need to transfer that data, those files to our system. Or if it's something you're pulling down, maybe from a GitHub repo, great. If it's a sort of closed source program and it's some commercial entity, then that's something that if it's closed source and you're not going to get access to the source code, there's no way to, we can't compile it. There's really nothing that we can do. I just want to check the chat real quick. When I request the interactive sessions, is there any upper bound number of hours for me? If you're using the open allocation, there's a upper bound of 48 hours. Since we're trying to sort of get our jobs to start quickly, it's best to have a small resource request. So small resource requests, including the number of hours. So that's why I said select 2, since that'll take us to the end of this workshop, beyond the end of this workshop. So I would say, in this case, use 2, but moving forward in the future, you can use up to 48 with the open allocation. If you're a member of a paid allocation, the limit is whatever your service level agreement is. So if you have an allocation purchase for 3 years, I mean, I guess technically you could have a wall time of 3 years, but we're going to have some service and maintenance in between there, so your job won't live for 3 years. But sure. Okay, so you need source code, you need a compiler. I mentioned that this option gives you as the user, you as the person building the software, the greatest level of control. the most dials or the most knobs to turn to in terms of optimizing the build. It's usually the most difficult and time consuming. It's up to you to handle all the dependencies, to turn all those knobs, to set all those options, and so on and so forth. But with that sort of extra effort, you can almost always get the best performance out of sort of compiling the code yourself. And I mentioned this can require some additional knowledge about the system you're running on. So some of the basics of compiling, it's generally best in recommended practice to compile on the same nodes that you're going to run on. So whether that's you open up a desktop session using the portal site on the node types that you're going to run on, or you submit an interactive batch job with this qsub-i. It's recommended to again, run on the same node types that you're going to compile on the same node types that you're going to ultimately run that compiled code on. Obviously, good to know which compilers you're using. So if you're loading a compiler with module load, GCC, you can use the which command to see where that compiler is located to make sure it's in the location that you know and you sort of you were expecting. And you can ask for version information, GCC-V or GCC-version to make sure the version of the compiler is correct. And I'm giving examples here for GCC. There's equivalent examples for Intel or PGI on our systems as well. So I have here an example compilation command, and we're going to sort of just step through this in detail here on the next slide. So GCC -capital O02 -lowercase o hello.out space hello.c and -lm. So let's sort of break this command down. So GCC is the GNU C compiler. So that's the compiler I'm using to compile some source code, which is in this hello.c file. Again, this is sort of abstract at this stage. We're just talking about some basic syntax for compiling a single source file. So GCC is the compiler. Hello.c is my source file. It's some hello world program written in C. Hello.out is the name of the compiled program. I'm specifying that I want my compiled program to be called hello.out. This -O2 is an optimization flag. So whenever you're compiling, there's many different optimizations or different options you can give the compiler. And -O2 is optimization level 2, which behind the scenes sets, probably tens to possibly hundreds of different options behind the scenes in terms of sort of tweaks and knobs with the compiler. So -O2 is one way to sort of just blanket set a bunch of different options or features for the compilation. There's different optimization levels, optimization level 0, 1, 2, 3. The sort of hierarchy with those optimization levels, in general, the higher the optimization level you use, the better performance you'll get. But that's not a hard and fast rule. It's sort of most of the time, but that doesn't always hold true. And also, the higher the level of optimization you use, the longer the compilation can take. Generally, it's best to sort of try 1, 2, and 3. And see what your code performs the best with. That sort of topic is for a later training coming up next week with our intermediate HPC in terms of different optimization flags and setting them and how to sort of choose the best one there. So that's something that we'd get into next week. And then our final option here with compilation is linking a external library. So -L lowercase l and then m. So m is the C standard math library that we're linking here. Okay, so that's our basic compilation command. With so linking, we saw in that example in the previous slide, dash lowercase l is how you can link a library. Another way is dash capital L, and you give a path to you give the directory path to where the library is located. Dash capital I, you can specify the path to a header file. On our system, we have many different libraries that you can link to. So MKL, Boost, PETZ, they're all part of our software stack. You can link different libraries that you write yourself, or things that you compile yourself. Some other helpful environment variables. CPath is another way to specify location of header files. Library path is an environment variable you can set to specify the location of libraries at link time. And then LD library path is how you can specify the location of libraries at runtime. So static versus shared libraries. So there's two different sort of flavors of libraries that you can sort of include or utilize whenever you're building software, whenever you're trying to sort of resolve a dependency of software. So for static libraries, the linker includes the actual sort of static library in the build. So whatever code is required is sort of built into the final executable. So this has the benefit of eliminating runtime dependencies. So if you can build some software in a way that it depends on nothing on the system at all, which can be difficult to do, then you can sort of more easily take that compiled program and move from system to system, or move from sort of location to location. So eliminating those runtime dependencies, it can take more time and lead to larger executables, what are sometimes called bloated binaries. I mentioned it increases that portability because, if you don't depend on anything, you can be much more portable, much more sort of transferable between systems. The other option is shared or dynamic libraries. So these require the linker, and these are required to be found at both build time and runtime. So sort of two dependencies there, static only at build time. This has the benefit of, let's say you are linking or utilizing some external shared library that does linear algebra. And then all of a sudden that linear algebra library gets updated, and you want to use that updated version in your code that you already have compiled. If that update is sort of compatible with the previous implementation, so nothing changed with how that library is used in terms of the API or the library functions, all you need to do is sort of swap out that library and sort of point your executable to that new library, and you can start using the updated library, that updated linear algebra library, without changing anything in your source code or even recompiling. So that's something that can be very attractive. And some other differences there as well in terms of memory consumption and things along those lines. Okay, so I just wanted to touch on those different types of libraries to make sure that you are aware of their sort of existence, and there are some nuances between the two, and sort of, when it comes time for you to investigate, you can sort of at least understand these two different avenues. So for help, real quick, this slide sort of gives some helpful commands for linking, finding those libraries. So I mentioned module show. If you, let's say you load the MKL, which is sort of Intel's linear algebra library. If you do module show MKL, it'll show you all the different locations where all their libraries exist, which you can then use whenever it comes time to link. The locate command can be helpful. Find command is sort of like the hammer on the nail solution, it'll exhaustively search the file system for whatever you tell it to. So locate only searches some predefined locations on the system. Also the LDD command. So if you do LDD and then the name of a executable or library, it'll give you everything that it's linked against. So everything it needs to find, everything it's expecting to find. This is sort of an oddball slide, and I'm not going to go through it in detail. Just know that our system is heterogeneous in terms of the processors that are installed on the different compute nodes. So what that means for you is if you compile your code to run on one specific node type, it may not run on any of the other node types. That has to do with those instruction sets that I was mentioning before. So what can you do? There's a couple options. Whenever you compile your code, you can sort of compile it in a way to make it compatible with all the nodes on our system, or you can define different, you can have separate compilations for each type of node that we have on our system, and then at runtime select the executable that lines up with the node type that you're on. So just keep this in mind whenever you're building and installing software. If you ever run into an instruction set error or invalid instruction set, this is probably your problem, and you can sort of come back and visit the slide, and it can help you out. Okay, so quickly I want to go over, I'm just sort of skipping ahead here. Okay, so we had our example GCC command where we saw how to some syntax for compiling a single source file. There's some tools that automate that process that are available in the public domain that help automate that system, that process, and can be very useful and helpful whenever you're trying to build and compile large sort of pieces of software. So hundreds of source files, many dependencies, those sorts of different software builds that you may encounter. So some common build systems that again automate this compilation process: Make, AutoTools, CMake, and also some projects just sort of hand out a manual sort of script that goes through the build process automatically. So with automated compilation, there's some obvious benefits. Automatically detecting your build environment, so figuring out what type of machine you're running on, figuring out what dependencies are available, figuring out what compiler is available. Some of these build systems, these automated build systems, do that for you without any effort on your part. Using a build system can increase reproducibility and portability, right? So if you have a defined recipe for how to build something, all you have to do is go back to that defined recipe and follow those steps, follow that through step by step. So sort of by design, it's makes it much more reproducible in terms of building your software again. I mentioned about easily handling projects, and it can make life a lot easier with whenever it comes time to recompiling. If you only change a single source file, if you're using Make, Make will only recompile anything it needs in terms of what change. It won't go through the entire sort of list of source files. It will only recompile what is required to make the changes. And some other nice options can come through build systems as well. So probably the one that most people have encountered, if you're sort of pulling down different repos from GitHub or any other sort of open source software, is GNU Make. So Make uses its own sort of syntax and has it has something called make files. And these make files are where you explicitly define how you build the software package. And these make files are comprised of 3 different parts. The parts where you define the outputs, the parts where you define the dependencies, and then the instructions for how to make each of those dependencies. So I'm just going to sort of go through an example of a make file here. So this is an example file. This is an example make file for building a target called factorial. We can see factorial has 3 dependencies. So it depends on object file factorial, readin var, and factcalc. And it tells us how to utilize those dependencies to build the factorial program. And then each of those dependencies has its own instructions for how to build. So 3 dependencies, 3 ways to, 3 instructions to build those dependencies, and then the final instructions for how to build the target factorial program. So you can see this is pretty simple. And then, I'm not going to delve into the complexities of make files, but in this particular workshop, that's something we touch on in the intermediate HPC, going in and sort of simplifying this a little bit more. But there's ways, if we had thousands of source files, we don't have to have thousands of lines, each building each line for each dependency. We can sort of encompass that with sort of 1 or 2 lines. So these make files can be very helpful in terms of simplifying the work on your end. And you can see that they're self-documenting, right? This tells us exactly what we need to do to build this program. There's no ambiguity. There's nothing that's sort of left unchecked. So in terms of reproducibility, make files can be very helpful. Auto tools are sort of 1 step up from that. So auto tools with configure maybe is another another sort of build system that you may be familiar with. And what configure does is it really generates your a make file for you. So you don't necessarily even have to interact with make files. CMake is sort of a cross-platform version of make, which is sort of continues to gain traction as well. So again, just giving you sort of a flavor of different automated build systems that you may encounter in sort of the open source world, at least. Okay, so now we're going to hit on our manual compilation example. So going through and utilizing, putting to practice some of the things that we just talked about. So hopefully all of you who have sort of submitted an interactive desktop session have that running now. So if you go to this interactive desktop and click the blue button, that should launch you into your interactive desktop session. Once you do that, if you go in the upper left and click Applications, System Tools Terminal, do that to launch a terminal. And then finally, we need to copy over our example files. So the way that you can do that is first, once you open the terminal, I want you to CD to your Scratch directory and then copy over the files by issuing this command here that I'm highlighting. And remember to include this trailing period here. So I'll pause here, let everyone sort of catch up to this state. If you have problems or questions, unmute yourself and let us know. If you run into a situation where your job hasn't started yet, definitely let us know that as well. So I'll leave this slide up for a minute or so, and then I'll go through this process myself in my own interactive desktop session. So you can follow along there as well. So I'm just going to come here now. So I open up a terminal. So File, System Tools, Terminal. I'm going to CD to my Scratch directory. And then if I do a CP dash, oh, I see a chat come in. Ready. Okay, so it looks like people are able to pull that over. So CP-RL and then this directory path here. If you hit enter, that'll copy that directory to your Scratch directory. It may take a couple seconds to do. If we then enter into the software seminar directory, you can see here a README file, so cat ICDS. This gives you a sort of just a text-based overview of the hands-on items that we'll be doing today. I just have this here if you sort of run into any issues, and it could be helpful to sort of copy and paste. You know, it can be a little bit challenging to copy from the actual presentation slides into the desktop terminal. So I just have this text file here for that. So if we go into compilation example, then we're sort of caught up with our slides. We can take a look at this this hello.c file, and it's just a hello world with also calculating some square root values. So nothing too complex there. So let's go ahead and try to compile this program, compile this source code. So what we can do is we can load the GCC 7.3.1 compiler, and then just issue GCC hello.c. So if we do that here, so I'll do a module load GCC 7.3.1, do module list to make sure I have that loaded, and then I'll just do a GCC hello.c. Okay, so it looks like we have a problem. So I'll go back to my slides here. We see here that the problem is it's complaining something about square root. It seems like the square root function is undefined. If we go back to our source code, we're definitely using, we're using the square root function. But we never define that. And so we're expecting that function to be defined in an external library, but we don't link that external library. So the fix for that is to link the external library that has the square root function defined. So if I come back here to my terminal, if I just do gcc hello.c-lm, that will link the appropriate library that has the square root function defined, so then we can run the program. So if you don't specify the name of your output with the -o flag, by default, it'll be called a.out. So that's what I have here. And then if I want to run that compiled program, I can do /a.out. You can see it'll say hello, and then calculate different square roots from 1 to 19. So integers from 1 to 19 inclusive. So that's a simple example of linking an external library, the C math library, an example of, if you ever run into a problem where you're getting some undefined reference, it could be that you're, not satisfying an external dependency. So any questions? I don't see anything in the chat. Hopefully everyone was able to sort of reproduce that. If any questions, let me know. I'll sort of just continue on to our hands-on example with lamps. So throughout the rest of our hands-on examples, we're going to be compiling or attempting to compile or use lamps. And lamps, for those that don't know, is a open source molecular dynamics software package that's written in C++ from Sandia National Labs. So, why did I pick lamps? Well, I wanted to sort of standardize on the software that we're using as we go through compiling from source, compiling or getting the software installed with using a package manager, and using the software, getting the software installed using Singularity. So I wanted to have a sort of uniform software across those different options. And then I also wanted something that was obviously open source because we want to compile it from source. And I wanted a large project so that this is thousands of source files in terms of size, and it can have many different dependencies. And it also ships with good documentation and an excellent build systems. And we're going to take advantage of the make build system. And as you unpack this these source files, you'll see that building this by hand would sort of be a little bit of a nightmare. Okay, so this slide summarizes the steps that you need to take to compile compile lamps with Make. And again, don't get hung up with sort of knowing or understanding what lamps is. Just know that lamps is this sort of software that we're using in order to sort of standardize across these different approaches for getting your software installed. So again, we're going to use Make, we're going to use Conda, and then we're going to use Singularity, all to bring this same software package onto the Roar systems. Okay, so let's go through this and get lamps installed using Make. So what you want to first do, and maybe I'll just sort of bring up my terminal and do this sort of side by side. So I'm going to exit the view here. Okay. So I'm just seeing which node I'm on. I'm just going to hop over to that node. So SSH. Okay. Okay, so I'm going to cd to my Scratch directory where I have these files stored, where we copy them over. I'm going to go into software seminar and then lamps ex. So the first thing I'm going to do is sort of extract this. Okay, so that's done. Now we can see we have a lamps directory. So I'm going to go into that lamps directory. So lamps 7 aug19 into the source directory. I'm just going to do an LL, and you can it looks like my terminal is sort of cutting that out. But if I do, I'm not sure what's happening here. My terminal is sort of hanging for me. Okay, so so you can see in this directory, there's 186 sort of source files, including headers. So that, pretty large software project, and that's with only the default options. There's many different options that we could include. So we have our source code. The next step is to make sure our environment is properly set up. So I'm going to do a module purge and then a module load GCC 5.3.1 and then OpenMPI. I'm going to do a module list to make sure that came through, and I see both of those loaded. Okay, so now we can take a look at the make file that we're going to use to build lamps. I mentioned, so lamps comes with many different build systems. It has you can use Make to build it, CMake. It also has a Python build system. We're going to take advantage of the Make build system, and it ships with a Make file that doesn't need to be modified at all, which is great. So if you want to view that, you can just take a look at that. If you do Make options and then makefile.g++ and OpenMPI, and here's our Make file. You can see it's a little bit more complex than our factorial example, but up here we're just defining some variables that will be used later, defining some of these external dependencies such as MPI and so on and so forth. So this is the Make file that we're using, and in order to start compiling with that Make file within lamps, all you have to do is type Make and then the sort of the compiler and MPI implementation that you want to use. So I mentioned we're using G++ underscore OpenMPI. That'll tell the system that we want to use this Make file, makefile.g++ underscore OpenMPI. So if I hit enter on that, that's going to start the build process using that Make file. And you'll see eventually this will start sort of ticking along, compiling each of those individual source files, and then ultimately linking those together. So this will take, I don't know, a couple minutes or so. So at this stage, I'll pause. If everyone is sort of having problems getting to this stage, let us know, and we'll address that. If I don't see any questions or anything come in, I'll probably sort of continue on, and we'll let this sort of keep compiling in the background just for the sake of time. But while this compiles, I do want to mention, we're using this stock makefile that ships directly from the LAMPS developers. There's some ways, we can go into that that makefile and start doing some customizations. So one customization with the GCC compilers would be to target the architecture that exists on ROR. So we could define march as Ivy Bridge. So this would be the lowest sort of common denominator in terms of processors on our system. And this would tell the compiler to at least try to take advantage of the AVX instruction set. That's not something we have time for here, but this is sort of just an example of how you can modify that makefile in order to make your compilation more optimal for the system that you're running on. And you would make that modification to the CC flags portion of the makefile. Okay, so I'm just going to check the chat. If we don't have any questions or issues come in, I'm going to sort of move forward. What if the instructions of the code include pseudo privileges? So you as the general user do not have the ability to invoke the sudo command. So if the software project that you're trying to use tells you to install the software, you run sudo apt-get name of the package or sudo yum install name of the package, that's something you're not going to be able to do. Just for obvious security reasons, we can't have general users of the system invoking those sort of root level permissions. So in those options, so if the software that you're trying to install only sort of has that as the available option, we could check and see if they have the source code. If they do, we can compile that ourselves. That way we don't need sudo. If maybe it's available through a user level package manager, which I'll touch on next, then maybe we can install the software that way. If it's only available through some sort of system level package manager like apt or yum, then our option would be to use Singularity, because within Singularity, when you build a Singularity container, you have the ability to use sort of sudo to install packages. So without knowing exactly what sort of package you're after, so if it's apt-get, we would need to look into where that software exists. Maybe it exists somewhere in open source form and we can compile it ourselves. If not, I would say let's just use Singularity. And I see you commenting that you have many dependencies. So I would sort of default into using Singularity, just because within Singularity, you can invoke those system level package managers, and those system level package managers are very good at resolving all those dependencies. If we had to build that software from source, we would be building all those dependencies ourselves. And so that's something we'll touch on later, sort of in the last portion, how to use Singularity. But yeah, great question. So I see over here on the right, my LAMPS build has finished. So hopefully all of you are on the stage as well. So this is building software package with make. And our test for LAMPS isn't going to be too exhaustive. It's just going to be, does LAMPS throw a help menu? So we're going to do that with the, we're going to call the name of the program that we compiled with, as you see here, and then pass the flag -h. So we can see, yes, indeed, it prints the help menu. So that's the test that we have successfully installed our software. Not very rigorous, but that's sort of not the point here. We're just sort of trying to make sure we have some level of functionality with the installation. Okay, so back to the slides here for a couple minutes. Okay, so that sort of rounds out our compiling software from source. Moving along to user level package managers. So and I sort of touched on a lot of these aspects with the latest question that we had come in through the chat. So what package managers aim to do, they aim to automate or completely manage the process of installing software. They automatically they aim to automatically handle those dependencies. You know, if a dependency is required and isn't met or doesn't exist on the system, the package manager will go out and automatically grab that dependency for you, install it, and make it available. Using package managers, again, it's sort of one step up from using a build automation system. So it's right there in terms of reproducibility and portability. And depending on the package manager that you're using, it may it may install software from source, or it may be just simply installing something that was already precompiled by someone else. So pulling down what we call precompiled binaries. There's different types of package managers, which I just mentioned. There's system level package managers. So Yum, if you're from sort of CentOS or Red Hat OS, apt-get with Ubuntu, DNF now with Fedora. These all require root. So on our system, you're not going to be able to do that. And that's sort of a full stop, you know, for the obvious security reasons. There's also generic package managers, which aren't necessarily tied to a particular language. SPAC is one, Conda is another one, EasyBuild another. And then there's software specific package managers. So pip for Python, PKG for Julia, CPAN minus for Perl. R has several different package managers as well. So there's these different flavors of package managers, and each of them can make your life easier in terms of dealing with software. So we're gonna go through an example of using Conda, and we're gonna use Conda to install lamps. So Conda, a lot of times people associate Conda with the sort of Anaconda Python distribution, but Conda isn't necessarily Python specific. You can, you know, it's a generalized package manager, and people make packages available through Conda that have nothing to do with Python. So on our system, at least, to get access to Conda, you need to load our Anaconda module. So these steps here will take you through creating a Conda environment, which is sort of, you can think of an isolated instance of Conda. Or Conda environments are very nice if you have different projects you're working on, and those different projects have sort of conflicting dependencies or conflicting sort of environment needs. You can sort of create silos of different sort of software installations very easily with Conda. So what we're going to do here is create an isolated Conda environment so that it doesn't interfere with anything else that you may have installed, and then install lamps within that Conda environment, and let the package manager handle all the external dependencies. We don't have to do anything, we'll see, and we'll just sort of rely on Conda to do all the heavy lifting. So I'm gonna sort of pull up here with my terminal again, sort of side by side with these instructions, and go through this. So I'm gonna leave my the current directory and back up into just this main software directory. So the first thing I'm going to do is purge out the modules, and then I'm going to load in that Python 3. Next, I'm going to use Conda to create an environment. So Conda create -n, and then you can name that environment anything you want. I'm going to name it lamps-env, and then I'm going to answer yes to any of the questions that are asked. So this will go through and go through the process of creating this environment. Since I'm not really installing anything into that environment, it should take really quick. So after my environment's created, it's telling me to activate my environment. So I can do that with source activate lamps-env. So here, so whenever I do that, you'll notice that my command prompt has changed. It's now prepended with this lamps env, sort of telling me that I'm inside of my lamps env con environment. So now the next step is just install lamps. So conda install. We want to install this from the conda forge channel in lamps. And then again, I'm just going to answer yes to everything that's asked. So this is going to have conda reach out within that conda forge channel, locate the lamps package that's compatible with a system I'm using, and then figure out all the dependencies, pull down all of those as well. You know, all with really no effort on my part, right? We're running a single command, conda install. I don't need to know anything about how this was built or where it was built or what it depends on. I'm just trying to, you know, we're just simply conda install. So while this sort of churns on my end, hopefully everyone is at the stage. But again, if not, unmute yourself, let me know, throw it in the chat, and we'll get any questions or issues addressed there. So you see that conda is now sort of solving those dependencies, figuring out what it needs to pull down, what's compatible. There's many different channels available through conda. You know, conda forge is a very popular one where there's you know, many different packages available. So I think you can just go to like Anaconda, Google Anaconda, and then the name of the package, and then that will give you a good sense of whether it's available through conda or not. Once we see this installation complete, we'll be testing our lamps installation again to see if it throws that help menu. If it throws that help menu, that's our sort of gold standard test that we're using today. Yeah, so right now I'm installing lamps through conda. Are you able to see my terminal? So hopefully that's being shared as well. Yeah, okay, yes. So what we're doing in this step is we're creating a conda environment using, you know, by completing these steps, and then we're using conda to install lamps. So here's our conda install command. So it looks like that's taking a couple minutes. Maybe for the sake of time, I will push forward, and then we'll come back and revisit this. Oh, there it is. Okay, so it's telling me, you know, in order to install lamps, we need all of these other dependencies. So it's going to install those as well. You know, some of these are met on the system, you know, but conda is sort of, because we haven't told conda anything, we haven't necessarily loaded any of these other items into our environment. Conda is sort of pulling down the whole kitchen sink. Everything it thinks it needs that's sort of unmet, it'll pull down for us. And you can see that, you know, none of these have anything to do, you know, I guess pip is associated with Python, but, you know, certainly MPI is something independent of Python. So conda is this generalized package manager. So once the command prompt is returned to you, that's an indication that your conda install command is complete. So now I should have the lamps command available to me within my conda environment. And if I do lmp underscore MPI, that's the name of the lamps binary that was installed with conda. And we can see if we get a help menu. And indeed we do. So we can deem this installation of lamps successful with conda. Okay. I will note that, you know, there's nothing that we could do in terms of, there's nothing that we did at this particular stage to specify the version of lamps that we wanted. There's nothing we did to specify how we want lamps to be compiled. All Conda did was reach out and grab something that someone else already compiled. So we're stuck with however they compiled lamps. So if they compiled lamps for some instruction set that our underlying CPUs can't take advantage of, then whenever we actually try to run lamps, it will fail. Or alternatively, if it's compiled in a very generic way to run on any system, we're not going to get the performance that we would get if we sort of went in there manually or sort of with make to dial in some of those options. But, that's the price you pay for a very simple installation, Conda install. Pretty simple. Okay. So, and then once you're done with that, you can exit your environment with source deactivate, and that'll bring you back outside of that Conda environment. Okay, so moving along here to our final sort of software install option, or your final option in terms of getting your software running on the ROR systems, using containerization. So Singularity is a container system developed specifically for use in a high performance computing environment. And it's comprised of two different pieces. There's the component that generates the container images. So these self-contained entities, which inside have all of the software and all the dependencies and everything that you need. And then the second component is the runtime. So the portion of Singularity that executes or runs the containers that have been built. So one way to give people an idea of what containerization is but it's sort of incorrect. But you can, as a first approach, you can sort of think about containers as a way to utilize a virtual machine-like environment on an HPC system or on any system that has Singularity installed. So with containerization, you can sort of, inside the container, you can be running a different operating system than what is installed outside the container. So the ROR systems are currently Red Hat Enterprise Linux 6. We're currently upgrading to RHEL 7, but you can run a Singularity container that has Ubuntu 16 or a CentOS 6 or 7. So you can sort of mix and match, and that's a way that we've relied on Singularity to get rid of to get around some operating system level dependency problems. So this is so Singularity is useful in dealing with dependencies, and this addresses the question that we saw in the chat a little bit ago, because at build time you can take advantage of those system level package managers. So you can run apt-get or yum install and have those tried and true, tried and tested sort of system level package managers pull down everything you need to install the software. Singularity by design, these containers are meant to be reproducible. There's a Singularity recipe that you can use. Whenever you're building containers, it's recommended that you do so by using a recipe file, and that recipe file is sort of self-documenting. Line by line, explicitly state how you want to build the container. And these containers are meant to be able to build them once in one location and then take that container from system to system to be able to run it. In Docker is another container implementation that you may have seen out in the wild. Due to security sort of constraints with Docker isn't available on most HPC systems, but Singularity can convert Docker containers directly to Singularity containers. So really all is not lost there. You can sort of indirectly use Docker containers just by simply converting them to Singularity containers. Scilabs is now the commercial entity that sort of manages the open source Singularity implementation, and they have really great documentation there. And also our user guide has some a Singularity component as well. I'm going to pause here because I see a question come in the chat. Nope. No question. Okay, so that's just a little background about containerization. I think it's something that can both address the problem of reproducibility in terms of software, and also reproducibility in terms of computational science, right? If every publication was required to ship with a container that had all the software and all the input and everything you need to sort of reproduce that the results of that publication, I think that would go a long way in terms of addressing the problem of scientific reproducibility, at least in the sort of computational based fields. So I don't think containerization is something that's sort of going away anytime soon. It's really great that we can utilize that on our system. So now we're going to take a look at utilizing containerization, utilizing Singularity to get lamps running on our system. Okay, so I'm going to, as I did before, I'm going to sort of minimize my slides here and sort of execute on those sort of side by side with my terminal. So the first step is to enter into the Singularity example directory. And we see in that directory, we have a couple files, and we have this CentOS 7.simg. So this is a CentOS 7 Singularity image that has been pre-built for you. So you don't have to worry about how do you build a container or anything like that. So one thing I want to show, I want to run some commands before we enter into the container, just to sort of convince you that yes, our environment has changed, and yes, sort of effectively our OS has changed. So one command that you can run on a sort of Red Hat like system to figure out which version of the operating system you're running is this cat command that I have here. So if I run that, again, I'm outside the terminal. I'm outside the container. I'm seeing that the operating system is Red Hat Enterprise Linux 6. Our version of the C standard library, one way to get that is this command here, this LDD -- version, and we can see we're version 2.12. Okay, so Lamps is available through Source. It's available through Conda, and it's also available just as a precompiled binaries. So, it's sitting on a server somewhere, and you can directly download the files and try to run those files. Try to run that executable that's been compiled. So let's try to do that here and see what happens. So before we do that, we need to alter our environment slightly. So we're going to do that with this source command. So we're going to source, again, before I run that, make sure you're in this Singularity EX directory. And then we're going to do a source /bin. And then this file called source me. Okay, so I already pulled down this precompiled lamps binary, and it exists in this bin directory. So let's try to run it and see what happens. So if I do /bin LMP and then try to get the help menu again with our sort of gold standard test, we see some problems. And the problem is it's complaining that our glibc, our C standard library, is too old, right? It's saying, it needs at least 2.14, and we know from what we just said, we only have what we just ran. We only have 2.12. So really, this is sort of a limit of the version of our operating system. So however this version of Lamps was compiled that we're trying to run, it's not compatible with a Red Hat Enterprise Linux 6 operating system, at least in its current state on our system. So what can we do? So really the easiest thing to do is to try to run that same compiled Lamps, that compiled program, from within a Singularity container, where inside of that Singularity container, we effectively have a newer operating system. So let's go ahead and enter into that Singularity container. And the way that we do that is we do Singularity shell, and then the name of the container. So CentOS 7.simg. So if you issue that command, it'll take a couple seconds, but eventually you will be inside we have some users commenting that this glibc error is an old friend. So yes, this is a common occurrence, and Singularity containerization is one way sort of around that. So Singularity shell CentOS 7.simg, we'll let that load for us. Shouldn't take too long. While we wait, again, if you have any questions, let me know. We can try to address those. Generally, it shouldn't take this long for a container to be loaded. I guess there's a few reasons why, but we'll just sort of wait here. Oh, there. So my command prompt has been returned to me, and I am now sort of inside the Singularity container, as we sort of say. So the first thing I want to do is let's check and see what's changed. So in terms of that, are we effectively in a different operating system now? So if I do that same cat command, sorry, this Zoom menu came down on me. If we run that same cat command, we can see now our OS is being reported as CentOS 7.7. If we run that same LDD command, we're seeing now it's 2.17. So we should be able to run that LAMPS executable that was just pulled down, because now we effectively have a newer version of glibc. So if I just do let's see where we are. I'm still in that Singularity EX directory. So let's just do a /bin, same command, and see if it works. See if we get our help menu returned. And great, we did. So this is an example of using Singularity containers. So you know, everything, the program that we're trying to run is stored outside of the container. It's on the file system. You know, we can access that version of LAMPS outside of the container. That's what we tried to do whenever we ran it and got that glibc error. We're just sort of using the container as sort of a runtime environment for the files that are stored outside of the container. It's sort of a popular use case for getting around glibc errors. So we have a few minutes left. I see a question come in the chat. Maybe, what will the usage of Singularity impact the computational efficiency? So this is something that's been tested. There's some papers available on this. In general, so while there is a little bit of overhead in spinning up those containers, generally that is negligible, and the computational efficiency or overhead associated with using a container should be minimal. You know, it's really a software specific sort of question, but these have been tested across many different systems, across many different types of software, and even in high performance computing environments where these Singularity containers are used in a distributed fashion, where, you know, using MPI, and the performance sort of holds up very well. So hopefully that addresses that question. Does it only use part of the resources? I'm not sure what you mean by does it only use part of your resources, but maybe I'll just sort of, if you want to specify, but I'll sort of try to comment on that. Unlike a virtual machine, you don't sort of say, I want to spin up a Singularity container with 5 cores or 10 gigabytes of memory. It's whatever you have accessible within your job. That's what's accessible from within your Singularity container. So if you have a job where you requested 10 cores and 100 gigabytes of memory, that's what's accessible to your Singularity container. You will always need the container to run the program. So yes, so in order to run the container, you need the container itself. So that file, you'll have to transfer that from system to system, and you also need Singularity installed on the system where you're trying to run that container. So those are the two requirements. But like I said, Singularity is becoming very popular and widely adopted, at least at different sort of computational facilities. So, you know, it's most likely going to be available if you want to run in other locations. Where can we find containers? So we have some containers available on the system. Jason has a link to a GitHub where he has some containers. So far, it's sort of there's some so far on our system at least we have not sort of created at least gold standards in terms of containers, but there's a few different places sort of outside of Penn State, outside of Roar, where you can look for containers. One is Singularity Hub. Another is cloud.scilabs.io, which Jason linked. Those are both sort of public Singularity registries where anyone can upload containers, and you can readily search those and pull them down. Another thing that I would suggest is to look at Docker Hub. So Docker Hub is a registry for Docker containers, but remember I mentioned that you can directly pull down and use Docker containers as Singularity containers. So feel free to shop around on Docker Hub as well. I think I have some links to those at the end, but if not, Jason linked the Scilabs sort of cloud platform, cloud registry, or the Scilabs Singularity Container registry, sorry. And then Singularity Hub is another one. Just to sort of give you guys an idea of what these recipe files look like. So, two options: either you pull down a container, you use a container that someone else sort of made, or you create your own container. So from within, I'm still within the container. If I run this command, we can see what this recipe file looks like. And we can see these are really just, so here's my container recipe. And let's see here, at the very top, I'm doing a bootstrap from Docker. So this is pulling down a Docker file, a Docker container, and converting that to Singularity. And that Docker container comes from NVIDIA, and it's a Docker container for CentOS 7, and it contains CUDA and all sorts of stuff. So we're bootstrapping off a Docker image that exists, pulling that down, converting that to Singularity. And then you can see I'm invoking a bunch of different yum commands. So this would be where you would, if you're bootstrapping off Ubuntu, you would do apt-get to install anything else that you needed that wasn't already pre-installed, and so on and so forth. So these container recipes are just sort of really shell scripts. I'm going to exit my container. For some reason, I typed exit. Okay, and then type exit to get out. Okay, so we have about 2 minutes left. So one thing I touched on, we use Singularity shell. That's how you enter into a container. You can also do Singularity exec. That will execute a container, as a command that you give inside the container. So maybe I'll do that very quickly here. So if I do Singularity exec and then the path to my container, CentOS 7, and then let's just give a command. Let's do cat etc release. So from what we know, that should eventually print out that this is CentOS 7. So we'll come back and visit that in a second because that has to start up the container again. So hopefully everyone's back on the slides now. Moving on, where to go from here? We have our user guide. We have a YouTube channel, and also Rise team and iAsk Center. You can contact the iAsk Center for any questions. If you're looking to get started with containers, that's a good place to start. Also, our user guide has some information. In terms of training, where to go from here? We have a HPC training series next week, which sort of takes some of these concepts a little further. We also talk about version control. We talk about profiling and debugging code. With our profiling example, we identify a hotspot in some code that does some matrix multiplication, and then we optimize that portion of our code by linking to an external library that's highly optimized for matrix multiplication. So that's coming up next week. If you're interested, click that here button. That here, underline here, will take you to the sign up sheet. Next spring, in terms of offerings, we're going to have some offerings through our Topic of the Month series. So software reproducibility and portability with containerization. That's taking some of these concepts with Singularity that I mentioned and sort of properly treating them and giving them time in their own sort of dedicated workshop. So we'll go through, exactly what is a container, how do you build one yourself, what are some different ways that you can use them, sort of a much deeper dive as opposed to what we touched on here today. Also, next semester, intro to machine learning, and finally a parallel MATLAB and HPC workshop that we're looking to put on. And with that, I think we're almost right on time. I can pause here for a couple minutes for questions, and yeah, so thank you very much. And I see we have a couple questions coming in the chat. When I submit jobs using QSub command, should I connect to the ACIB node via SSH before QSub, or can I? So you can do both. You can connect to a login node and do QSub from there. But if you already have an interactive desktop session, what you're calling an ACII node, you can QSub from there as well. So both, you can do both. Okay, I see a question coming in. Is compiling on the head node prohibited? It's not prohibited. It's just, so our head nodes, our login nodes, are virtual machines. They're not meant to do anything sort of heavy lifting. They're shared amongst anyone who connects. So, you could be sharing that node with 50 other people. So the compilation may go slowly, and it doesn't follow the rule of compile where you run at. So those VMs, those login nodes, may have may represent a different architecture or a different sort of processor that you would ultimately run on. But there's nothing stopping you from compiling on a login node. And for small builds, sure, I do it as well. But for larger builds that take a lot of time and larger builds that you may want to parallelize, I would suggest that you would use a interactive session for that. So if the code is not computationally intensive and you would like to run it on a login node, so generally you shouldn't run anything on a login node. They're really there to facilitate basic sort of file manipulation and basic file editing, not the execution of code. Now, if your definition of code here is moving a file or editing a file or some sort of like post-processing step, sure, go for it. Yeah, you'll be okay doing it there. But for in general, computationally intensive, IO intensive tasks should be run on dedicated compute nodes. Will this recording be uploaded to? So it won't be uploaded to YouTube, but this session is being recorded, and as soon as Zoom makes that available to me, I will follow up with everyone that was registered, and either myself or the communications team can send the sort of Zoom link of that out, and that can be shared. You can share that with anyone that you'd like to share that with. Okay, so I don't see any other questions coming in the chat. Again, thank you very much for your time, and I will follow up with the recording of this as soon as that's available. And again, if you're interested, please join us for the session next week, sort of delving a little deeper in using ROR and using our systems in an HPC environment. Thanks.